Okay, the next video is from section 10.5, where we really are starting to get into some of the new stuff that you probably have not seen before with the equations of lines and planes. And we're talking specifically vector equations of lines and planes in 3 dimensions. Okay, so you're used to lines in 2 dimensions, used to planes in 3 dimensions, what we would call like the scalar equations, and we're going to talk more about the vector equations there. I'm going to do it in 2 videos. So video 1, we're just going to talk about lines, and then video 2, we'll talk about planes. Okay, so we're going to start out here. The equation of a line in space is a vector. And R is what we will typically use as a position vector. So it will tell you basically what position you are on the line. In terms of a parameter, T, and if you remember back from Calc BC, we did a lot of correlating vectors to parametric equations, just kind of talking about how they're the same thing. A vector equation gives you the components of basically a parametric equation. And that position vector, then if you plug in different values for t, you'll get every point on the line. Okay, so kind of a visual of that, if we have our 3D coordinate system here. Okay, and then maybe we have a line going through space. Okay, and we would have, maybe, and remember, all of your vectors, we assume standard form, right? So maybe this is R of 1, R of 2, right? And so this would be an equation, R equals, and I'm just going to put it really general, okay, some relationship with T that no matter what you plug in for T, it will give you some point on that purple line, okay? So your general idea here okay, so R will be some known point on the vector, okay, plus TV. And so I'll define what V is here. So R naught is the position vector of some known point on the line. And then V is the direction of the line. And hopefully when you see this, a light bulb kind of goes off, where we see that this is kind of like intercept. And this is like slope. Okay, so basically we need to know, where do we start? Where's the starting point? And where can we move from there and stay on the line? Okay, so we'll just do kind of a quick example here. Do example, find the vector and parametric equations for the line that passes through the point -2, 5, 1 and is parallel to the vector 3i minus j plus 2k. All right, so we need to know a point on the line and we need to know a direction. Okay, so that's exactly what we're given. We have this point. Okay, so we write it as a vector. Position vector of the point would be negative 2, 5, 1. And then the direction vector for the line, if it's parallel to the given vector, the direction vector would be 3, negative 1, 2. Okay, so remember we would have r equals r naught plus tv. So it's going to equal negative 2, 5, 1 plus t times 3, negative 1, 2. Okay, and what we generally do then is we want this to be a single vector. Okay, so we simplify it here a little bit. So we'd have negative 2, 5, 1 plus 3t, negative 1t, 2t. So we'd have negative 2 plus 3t, right? We're just vector addition here, right? Just add the components. Okay, so there would be the vector equation, right? The vector equation. In component form, you can also do linear combination form, which you see a lot of times in your textbook. Your textbook is a little bit more formal, but they like to use the linear combination form. And remember, this would be vector r. Okay. Okay, so there's your answer. It does ask for parametric, so your parametric form would just be x equals negative 2 plus 3t, y equals 5 minus t, and z equals 1 plus 2t. Okay, there is another form, which would be the symmetric equations. And that just eliminates the parameter. So we could take your x, and x plus 2 over 3 would be t. For your y, let's see, we would do t equals 5 minus y. Okay, and then for your z, minus 1 over 2 equals t. So your symmetric equations would be x plus 2 over 3 equals 5 minus y equals z minus 1 over 2. Okay, so there's the three different forms you might see: your vector form, your parametric form, and your symmetric equations for a line. Okay, one more addition here is if we want to do a segment. So we don't want the entire line in space, we just want a segment. All we need to do is limit t. Okay, so if we look back again at our example, if we just wanted the segment from negative 2, 5, 1 to, let's see, look at that direction vector again. Okay, if I just move 1 unit of t, so it gets me to 1, 4, 3. It doesn't change my direction vector, okay? It would just, I would just have the same equation, but just say for t is between 0 and 1, okay? There is, I mean, that would be, we'd have our original equation, which would be r equals negative 2 plus 3ti plus 5 minus tj plus 1 plus 2tk. And we would just say only for t between 0 and 1. Okay. When it's not as straightforward for that as that, like I just made it super easy where it's just one unit of t away. Another thing you can do is, so if you just have the 2 points, R0 is the position vector of point 1. R1 is the position vector of point 2. And it doesn't really matter. I mean, I'm calling them point 1 and point 2. I could call them point 0 and point 1 if you want to be consistent there. Okay. Then you get your position vector by just subtracting those, right? If point 1 is on the line and point 2 is on the line, then all I need to do is subtract those two position vectors to find a direction vector. So your direction vector would be R1 minus R2. Okay, oops, and I just switched. I just said you might want to be consistent, and then I wasn't. R1 minus R0. Okay, that tells you how to get from point 1 to point 2. You go in this direction. Okay, we don't know how far we go in that direction, but we go in that direction. Okay, so then when we have your general equation there, we can rewrite it as R naught plus T R1 minus R naught. Okay, and then we can distribute that T. And combine our R naught terms. Okay, so we would have 1 minus T R naught plus T R1, and then we would have T between 0 and 1. And that would get you your segment from R1 to R2. Okay, next video will be planes. Make sure you check out the examples in the book.